Hello everyone, my name is Dhruval and today I will be presenting my DA5030 project on developing machine learning model for diabetes prediction in the Pima Indian population. This presentation will walk you through my approach to model building, evaluation and insight gain throughout this project. The data that I use is the Pima Indian Diabetes Database, originally from UCI Machine Learning Repository, and that I downloaded from Kaggle. This data set contains medical and diagnostic measurement from female patients in Pima Indian heritage. It includes 788 observation with it includes 788 observation with 8 period variable and one target variable indicating diabetes data. The PR include pregnant is glucose level, then blood pressure, internet, insulin, BMI, diabetes pedigree, age. But I loaded the data and used button like aim and glim to get a comprehensive overview. One critically you added over what that meeting values were encoded as 0. The meeting value was encoded as a 0 in medical measurement, sometimes that needed carefully handling as a 0 blood pressure or glucose level is physiologically impossible. This visualization plot using plot intro and plot making confirm the data structure showing 788 observation across 9 variables. While formally there appeared to be no making value, the zeros in medical measurement implicate meaning that require attention. Moving to the data preparation, I handle the meeting value by applying domain knowledge rather than using automated method. I, I identified columns likely to have zeros representing mean values. Glucose, blood pressure, thickness, insulin, and BMI. I converted the 0 to NF values, then applied median imputation rather than mean imputation because it's more robust against outliers while maintaining computational efficiency. For peer engineering, I created a BMI age interaction peer based on medical literature, suggesting that age implied BMI's impact on diabetes rate. Then I applied minimum maximum scaling to ensure all the peer fell within 0 to 1 range, which is particularly beneficial for gradient based algorithm like XGBoost. After cleaning the data, I conducted peer exploration to understand which variable best distinguish between diabetic and non-diabetic patients. I created a bot plot. I created a bot plot by outcome group rather than using histogram because they clearly code both cattle tendency, different and distribution rate. As you a peak like glucose BMI and it or significantly different between diabetic and non-diabetic group. For correlation analysis, I use a color-based correlation plot because the color gradient may pattern immediately visible. This analysis code no major multicollinearity between predictor with beneficial for model stability. This is my code for peer exploration. For peer election, I implemented recursive peer elimination with 10 poll road validation to identify the most predictive variable. And here is how the plot looks. The result highlight the glucose, BMI, and age at the top predictor, with aligned with medical literature on diabetes risk factors. While I kept all peaked per model building, this analysis provided valuable insight into the peaker importance that helped validate later modeling result. This is how the variable distribution look like. Glucose 143 1 in 110 mg per L, BMI 35 1 in 30 kg per meter per average and an electronic current and effect with BMI. And this is how the correlation analysis look like. Now let's move on to model building. For model building, I deliberately constructed a diverse set of algorithm with different mathematical foundation to go through uh, to go thoroughly explore the model path. Uh, I implemented random forest for its ability to have a non-linear relationship and handle peer interaction. Then I chose attribute known for data part performance on structured data with complex patterns. Then I use GLMNet, that is regulatory logistic regression, as a baseline linear model offering interpretability. Then I use backtree to isolate the benefit of bagging separately from random picker election. And also use the attribute to compare against the attribute with a different voting approach. I choose 10-fold rot validation repeated 3 times rather than impulse holdout validation to get robust performance estimate. I optimize for ROE rather than accuracy due to the moderate large imbalance in the data set, with about 35% of it being diabetic. It will take time to run. It take around 20 to 25 minutes on a good machine to train the model. And we hyper tune the parameter for the optimization. We did are the parameter which we ran for optimization. Now let me demonstrate how the model perform on the data. It my code for the model evaluation. Let evaluate it. This is how the result look like. To standardize evaluation across all models, I created a custom function that produced confusion matrix, calculate accuracy, sensitivity, specificity, and AUE code, and the plot ROE curves. As you can see from the result, the Adabot model achieved the highest. Where is the Adabot? Arab, GLM, bag, Adabag. Yeah, as you can see from the result, the Adabot model achieved the highest AUE at 0.832, while random forest provided an excellent balance between sensitivity and PAPAD. The regularized logistic regression favored PAPAD. PAPAD uh, uh, but with more positive it is in a healthcare context where false negative are particularly problematic. To validate model performance more robustly, I compared cross validation result across uh, all models The analysis confirmed that Djibouti admittedly had the highest average ROEO during the training that 8.847 and followed closely by GLM and that about the not visualization or performance variability. Dr. Ample noted that the GLM had the lowest variability while Attribute had slightly higher variability despite its better average performance. This result aligned with my data at finding validating that the model performance trending was stable and not artifact of a particular data plane. To enhance the interpretability, I attempted be an important measure from both random forest attribute and attribute. This algorithm calculates importance differently. The random forest uses impurity is while attribute user uses gain or agreement between them and confident in the findings. Both models instantly identified glucose at the most the let in the result and I will let you understand what we are speaking about. Both the model strengthened confidence in the file. Both models instantly identified glucose glucose as the most important predictor, followed by BMI age and BMI, validating both medical literature and my peer engineering decision. To further understand how lipid in peer impact prediction, I created a partial dependent plot dependent plot for glucose and BMI. This plot revealed the clear non-linear relationship between diabetes rate increased dramatically and glucose values increased above zero point 0.8 on the normalized scale, corresponding to approximately 120 mg per dl in the original unit, which aligned with clinical diagnosis threshold. Finally, I created a majority voting enable combining random forest attribute and GLM. Uh, I chose this approach because it provided a straightforward way to combine credit and without it of overfitting. I deliberately selected a model from three different algorithm families to maximize credit and diversity. Interestingly, an enablement in the GLM performance and GLM performance that is 77.12% urine with 55.58% sensitivity. Instead of improving upon individual model that demonstrate that the model diversity alone doesn't guarantee improved performance. An important finding that challenges the womanism and that enable always outperform individual model. To summarize the e-latent, to summarize the e-binding and latent from this project, the data quality method identifying and properly handling meeting values was crucial for model success. Then the glucose BMI and age emerged as the most important predictor across all models. The three main enable method provided the best overall performance. The enable model didn't outperform the individual model. the ensemble model didn't outperform individual models, suggesting correlated error between models.